Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right. Hello, everybody. Well, welcome to another episode of Ask Us Anything About Electrochemistry. Neil's just coming in right now. All is good.
I'm not late. You're late.
Yeah, I am.
All right. Sorry about that.
No, it's all good. It's all good. Started. We're doing things a little bit earlier than usual. We typically live stream out at 1 p.m., but due to scheduling issues, we're doing it now early. But we already have some questions that are coming in. So
yeah, so we'll get right to it here. So
right
Shamim, you actually had a question, if I'm not mistaken, at the very end of our live stream last week that I have, and I'll talk about briefly, but I'll get to the one that you just asked right now first. So he says that today I did a CV experiment for my sample coated on nickel foam in half molar sulfuric acid in the range of minus 0.6 to 0.6 volts. You observed that the nickel foam is getting broken. Why is that? Should I choose too low of a potential? So I think it's one of two things. One of them is that I think you are going possibly too low in potential. So just doing a little bit of mathematics for you, for instance, the hydrogen evolution reaction, now maybe that's what you're trying to study, in which case, I mean, this might be just difficult fundamentally, but the hydrogen evolution reaction takes place at 0 volts versus NHE. Okay. So the phenomenon of potential with pH is that standard potential shifts minus 60 millivolts per pH unit, roughly. So what does this mean? Well, when the pH goes down, the standard potential goes up. And when the pH goes up, the standard potential goes down. So in your case, consider neutral of 7, whatever. Half molar sulfuric acid's like pH of 1 or slightly under 1. So let's just say it's roughly 7 pH units different, right? So the shift of where HER will start goes from 0 up 60 millivolts times 7 pH units. That's about 400, right? 400 millivolts, give or take. So now in mildly whatever concentrated or whatever sulfuric acid, the HER will take place in theory at about 400 millivolts, let's just say, versus NHE. Now you're using I think you said silver chloride reference electrode. Mm-hmm. So make sure my math is right, Alex. Right, 400 millivolts versus NHE is 200 versus silver chloride. Give or take. Is it 220? What is it?
The difference between is about 200. That's like
it's 2.1. Is it 240? For some reason in my head I always mix up AgCl and calomel. Calomel's 240 and AgCl is like 199, 200, right? I think that's right.
Yeah. So I know silver chloride is like 0.197,
so
and then 200, so it's about 200.
Okay, so I did do that.
So I think you did that correct.
Okay. So all of this is to say, after all of this talking through, is that the hydrogen evolution reaction, if my calculations are correct, will be taking place at, roughly speaking, 200 millivolts versus AgCl in half molar sulfuric acid. You are going to minus 0.6. That is about 800 millivolts of overpotential for where the standard potential might be for HER. That's a lot. So one possibility is that you are making a lot of hydrogen gas at the lower potentials, and there is some physical kind of disruption. Hydrogen gas is forming and it's breaking apart the foam. Depends how well it the adhesion is, I guess, of your sample and the nickel foam, maybe the gas bubbles are sort of breaking that up and causing it to break apart or something like that. That's one option. And so I don't know, you might have to adjust the lower potential window that you're doing. That could be one option. The other option is that fundamentally nickel as an electrocatalyst is more stable in alkaline than in acid media. I think there are some studies of nickel or nickel alloys, for instance, in acidic media, but nickel as a metal by itself is typically used in alkaline media because it's more stable. So nickel can undergo a chemical dissolution, for instance, in acidic media that is basically nickel. I'll try to draw this plus sulfuric acid. It'll dissolve to form nickel, essentially nickel sulfate, plus hydrogen gas. So it's possible it's dissolving, then you're making more hydrogen gas. This is a chemical process, not even an electrochemical one. But this will happen. Now, the rate at which this happens, I've seen a paper or so that says that it's relatively slow. It probably depends. If you have a nickel foam, it has a high surface area. A high surface area probably makes this reaction happen a little faster, or at least maybe it doesn't change the rate, but it's just that it's happening more because your surface area is greater. Like it might be causing problems. And so maybe the nickel foam is starting to dissolve in your acid. That's one possibility. Alkaline batteries, nickel metal hydride batteries, all of these kinds of batteries, for instance, that use nickel, they're all alkaline batteries because nickel is very stable in alkaline. It makes nickel hydroxide, nickel oxyhydroxide. These things are very stable. Nickel and acid is less stable. So it's possible you have some dissolution. I don't know exactly electrochemically. There might be an electrochemical, like at certain potentials. This is obviously a chemical, as I said, reaction here, but you might be oxidizing nickel at the higher potentials possibly. And so the nickel is going to, nickel 2 plus, for instance, plus 2 electrons. So that you might be doing that and oxidizing the nickel, and that's causing it to dissolve also. So you're pushing it electrochemically, it's happening chemically. I think there's some real stability issues, and so I would basically check into that. I don't know what the standard. I'm just gonna look it up just for my own curiosity.
The E-naught of
nickel. of nickel by itself. I don't know what it is exactly. Let me see if I can sort of just pull it up quickly here. Standard potential tables anywhere.
Mm-hmm.
That's trying to get me to buy something. I don't want to buy anything. I just want to look at standard reduction potentials. Let's see. Nickel is somewhere. Standard potential table. Let's see. Nickel. No, this nickel hydroxide. That's not the one that I want. Nickel, it's minus 0.257. So again, we could do the adjustments here. For example, this is going to happen at positive, let's just say positive for your situation, right around 0. So it is possible that once you go above 0 volts versus AgCl, you might be also oxidizing nickel to nickel 2 plus, and that's causing more dissolution. So anyway, all of that is to say, those are a couple of possibilities as to why you're seeing what you're seeing. And I would have a general idea of trying to avoid using nickel and acid, just as a general advice. It's more stable in alkaline media. Mm-hmm. And then I'll move on to this. Again, Shamim, you had asked again, I think last week, it was right at the end of our live stream. We didn't have time to answer it, but I'll answer it now. You asked, we have to set an initial potential while obtaining EIS data. What is the best practice to use OCP or onset potential? What amplitude is best to use? So yes, when you run impedance, you have to pick a set point to do the impedance at. What I'll try to say gently here is, if you're asking what potential you should do impedance at, take away the idea that you're doing impedance. So I would ask you, what are you studying? Like, if you're studying some particular reaction, for instance, okay, and let's just say you have some process that has a like cyclic voltammogram that looks like this, right? And let's say that the right here, this is the OCP like value. It's over here. Just what happens to be, whatever this value is. Okay. Well, if you are trying to study this oxidation reaction and you pick the open circuit potential, I would ask you, are you actually studying this reaction here, this oxidation? Right? I hope that you would recognize, for instance, if this is like 0 volts, right? And then this peak right here, let's just say, is 500 millivolts. Well, if I told you, okay, I need you to do a bulk electrolysis chronoamperometry experiment to generate some product that's created by this oxidation reaction, you would not pick OCP. You would pick 500 millivolts, or over here, you'd pick some potential where it's happening, because it's obvious to you. If I tell you generate product, you have to pick a potential where the thing is happening. So what I would ask you, as gently as I can, why would you think any differently when you're doing impedance? If you're trying to do impedance to study this oxidation reaction, why would you pick this potential? Why pick the same potential? It's the same thought process. Impedance is probing whatever it's probing at whatever potential set point you pick. So pick the set point that is where the thing you're trying to study is occurring. Simple as that.
Yeah, I would also just add, like, we usually get this kind of question a fair bit, and when I was at least learning impedance, one thing that was confusing, or I thought one of the reasons why, like, oh, you should do impedance at OCP, is that one of the conditions for impedance is that it needs to be stable, right? And so if you think about, oh, I'm gonna pick some potential where the oxidation reduction reaction is occurring, well, maybe the system isn't stable, but you can have systems to be stable, even if you're doing an oxidation reduction reaction. They just end up being at equilibrium over time. So so there are actually some very good comments from Tiwichi, who's just saying, like, the importance of the settling period. Yeah, as you let it sit for some time period at this 500 millivolts or more or higher potential for a while, and then you do your EIS, and the process is occurring at that point. So that's another thing. But yeah, that's you want to do that at OCP.
And then just the last part of the question, I think you said what amplitude to use. I mean, it really depends on, I guess, so to a certain extent, it depends on what will give you the best signal. So typically 5 to 10 millivolts is that range. That's a good place to start. It's not guarantee though. And it's to your point about the signal being stable and everything, with impedance, what you're fundamentally trying to do is give an amplitude that is large enough to perturb the system, but not so large that it's not linear or not stable. And that tends to be something that's like 5 to 10, sometimes up to 20 millivolts. If you go much higher, you will really perturb the system and you will get a good response, but the amplitude being really, really large will start to be nonlinear, and then your data are not valid. So start with 5 millivolts. You will not hurt yourself by having too small of an amplitude. You'll get, if you start with 1 millivolt, for instance, and the data is really noisy, you didn't damage anything, your data is just bad. So increase it slowly until you start to see the signal look more clean. If the signal isn't very clean, that's one of the things you can try to troubleshoot. Like you do 5 millivolts amplitude and it's kind of noisy. Okay, go to 10. It's still noisy, go to 15 until, eventually it might start to clean up. And run Kramer's Kronig on your results. That will help also identify whether it's valid or not.
Yeah. We just have a question that came in. This is,
Mm,
interestingly enough, I think it's along the same lines of what we've been talking about. But
mm.
Amna is asking, which technique is more effective to study water splitting for the oxygen evolution reaction? Either CV or EIS.
Both.
She wants to know, but between the two, which one would you pick?
Why does it have to be a fight? Why
It's
can't
true.
they? There's enough room in this town for both of us.
That is true.
It's not. Yeah, I don't know. I don't really know that there. I want to answer this question. To be honest, I'm not trying to avoid the question entirely, but that like it's. I read. I'm not trying to be rude or anything here. I promise, but I reject the premise of this question. Which one's more effective? This is not how we consider electrochemical analysis. You do all of the methods that will help you gain insight into your system. It's one isn't necessarily better than the other. They just give you different insights. The oxygen evolution reaction studied by cyclic voltammetry will show you the overpotential and the onset potential. You know, it's supposed to happen at 1.2 volts, right?
Mhm.
Theoretically, and if your current starts to increase for the oxygen evolution reaction right at 1.2 volts, you have a great catalyst that has a
Mhm.
very low overpotential. Like if you have a catalyst where you have to scan up to 1.5 before it starts running the oxygen evolution reaction, your catalyst is bad. It's slow kinetics, like the kinetics
Mhm.
aren't good on it or something, right? Like that's what cyclic voltammetry will give you. And, it will give you at whatever potential. A lot of times the metrics, I think, for like, publications, for example, are like at whatever potential, what is the current density you get? And that's like the metric. So it's like, at 1.4 volts, how many milliamps per centimeter squared do I get or whatever? And that's how you can kind of compare your results across other people's publications, et cetera, right? That's what cyclic voltammetry will give you. Those are all useful data, useful things to study. However, and as I think Sharif has added here too, EIS will give information about the charge transfer resistance. Exactly. So once you've picked a potential at which OER is happening, or you do EIS at a bunch of different potentials, you can track, for example, in conjunction with the overpotential, the onset potential, the current that you get. How does the charge transfer resistance change over potential? How do the diffusional effects are looking? What's the interfacial capacitance? Um, those are things that impedance will get you, but neither is better than the other. Like these are all complementary kinds of analyses. So I would encourage you not to think necessarily in this way. Like, well, unless you're sort of in the situation where like you get into the lab and you have like 20 minutes before the power is about to go out and you have to pick one of them, like is anybody in that situation? Like,
Oh yeah.
I guess, I mean, it's possible. Like you only have 1 hour to do your research. Like
Mhm.
that's not really, researchers would never leave the lab. It's sort of,
Well,
you know,
yeah,
like, is there a time constraint? You're not allowed to do more than one method, I
yeah,
don't get it. I
yeah.
don't really get the question.
But
That's my point.
we do know that some techniques are more effective than others electrochemically. So, like for
Sure.
example, if you're doing a very sensitive quantitative study where you're trying to detect trace amounts of something, differential pulse or pulse voltammetry
Mhm.
techniques are generally more effective than scan or linear
Yes.
sweep
The
things.
differential
Yeah,
current calculation
yeah,
will
differential current
detect
calculations.
smaller concentrations of things than cyclic
Yeah, then
voltammetry will.
yeah,
Yeah, that's
yeah.
certainly true.
So there are times where like uh a technique will be more or less effective. And there are things like, EIS, just as actually as the guy said, like you can actually, if you're putting like a film or something on your for your OER, catalyst or something, the state of the film can be analyzed with EIS. It's much harder to do that with cyclic voltammetry. So all the techniques have advantages and disadvantages. And in some cases, it's like, okay, yeah, one technique is more effective at one thing and less so at another thing. But to Neil's point, like, yeah, unless there's a time constraint. But sometimes there can be like a financial constraint because not all potentiostats have EIS. Most of them do, but you know, if you really want to get very, very good EIS data, Sometimes you need a more expensive potentiostat. And most cyclic voltammetry experiments, it's very, very simple. So sometimes there can be a cost element that's involved. But hopefully that kind of answers your question. I think Neil's answers perfectly fine. But let us know if you want more follow up on because if we know a little bit more about what you're doing, we may recommend you should do more EIS and less cyclic voltammetry, or you may need a whole different technique altogether. So there was a question from, let me see. I'm just reading this. Sheriff just said that an electrocatalysis is important for activation of your electrode before starting the LSV measurement. Yes, you can definitely do that for certain electrocatalysis systems, activating your system. So there was a question from last week from Mustafa from LinkedIn. And he asked, could you please explain the Dunn method, which used to determine the ratio of capacitive and diffusive behavior, and why, if the power of B is equal to 0.5, represents diffusive behavior, and if it's equal to 1, it represents capacitive behavior. Now, I'll be honest and open. I have always found the Dunn method to be odd or strange. It's not in this book per se. Alan Bard's book, but upon reading and so I tried to look deeper into this question to understand more about the Dunn method. I actually found there's very little formal textbook stuff, at least to what I have found. Maybe I need to do a little bit more digging that describes the Dunn method or pseudocapacitance specifically in more detail. But I did find a publication that I'll share with which I'm basing the rest of this stuff. So I think I'll share it from the window. So hopefully you can see this. I found this paper, High Rate Electrochemical Energy Storage Through Lithium Plus Intercalation Pseudocapacitance. And I believe Bruce Dunn here is the kind of person who created the Dunn method. And actually, we know Veronica Augustine. I don't know a lot of these people, but Hector Brunio is a very well-known scientist. And so I had a chance to read it, but the equation specifically you're looking at is this one. Is my screen zooming in at all, or no?
It's doing some weird thing. What happened to the?
I don't know what happened.
The top is there. We go. That's a little better. There was like white panels at the top. I'm not sure what's going on.
Yeah, I think what I'll end up doing is, instead of sharing this, I'm gonna share the PDF, because the PDF I think gives me a little bit more.
Yeah.
This is, I think, a little bit more.
That's better. Yeah.
This is better. Okay. So this is the equation that you're alluding to, where the current is equal to A times the scan rate raised to the B. And this B, as they mention, has a value of 0.5, which indicates current controlled by semi-infinite linear diffusion. And 1 indicates the current that is surface controlled. So my understanding, generally speaking, and I haven't looked at the complete derivation of this, is you can actually relate this to situations or systems. And let me see if I can't find the overlay. But so in the Cottrell equation, or not the Cottrell equation, but in the Randall-Sevcich equation, for a diffusion-controlled species, for just a simple redox system, you end up getting a square root of the scan rate dependence. And so this, the Randall-Sevcich equation, I actually don't know exactly how it is derived, but it describes how the peak current for a diffusion-controlled, specifically diffusion-controlled species, has a square root of scan rate dependence. And so there is this square root dependence when you have purely diffusion-controlled redox species in cyclic voltammetry. And then conversely, and actually I didn't draw this, but this is like my, a very, very, very simple equation, which is, where's my PowerPoint? is my PowerPoint not showing up here? That's strange. Sometimes
it's on the second page. Or
oh, it's on the second page. Yes, I have too many things open.
Yeah.
There we go. So the second equation, which is just that the current for a capacitor is equal to the capacitance times, and I'll just write this as kind of a dV/dt. The change in the voltage per unit time. I didn't have to use the right. So this is the equation that governs a capacitor. And actually, what I'll do is I'll put this, or actually, I'll put the Randall-Sevcich equation. I'll put the small form of the Randall-Sevcich equation next to it. Right. So, and this should actually be a new, if we're being, well,
is it epsilon?
It could, it's technically epsilon, but I like to put.
I always used to use nu. And
yeah.
Then, I was told it should be epsilon.
Yeah.
Because nu is kinematic viscosity. But
yeah.
they look the same.
They look the same.
One of them looks like a U, one looks like a V.
Yeah. Actually, this is actually correct.
That's better.
That's better.
That's a scan.
It's the scan rate, and this
because dV/dt is new.
Is new.
So it wouldn't be d nu dt.
Yeah, it wouldn't be d nu dt. So this is just how a capacitor behaves. So if you were to buy a capacitor, and let's say like a Radio Shack or DigiKey or something like that.
Does Radio Shack exist?
They do, but they mostly sell other things. Mm-hmm. So if you had a pure capacitor, so two oppositely charged parallel plates with a dielectric in between them, and one's positive, and then the other one is negative. If you were to do cyclovoltammetry of this, you would get these squares that would start to increase linearly with time, or linearly with the scan rate. So you end up seeing the case like when you have a pure capacitive system, there's a linear relationship, and it's just, so this is just new. But when you have a diffusion controlled process here from, say, the Randall-Sevcich, you have a nu to the 1/2. And so the equation where you just have current is equal to A times nu to the B, and then B can either be 1 or 1/2 or something in between, is just a way of describing how capacitive it's like, because it follows the equation for a capacitor, or how diffusive it is because it follows the equation for from the Randall-Sevcich equation, where you have a square root dependence on the scan rate. And so, yeah, in that paper, they had values of, say, 0.7 or 0.8. Some of these pseudo capacitor systems seem to have interesting properties. It's not purely diffusive, it's not purely capacitive, it's something in between. And these are systems where, like, you actually can store charge just like a capacitor, but you can also dissipate that charge through an electron transfer. So still learning more about pseudo capacitance and stuff like that. And let me just see. Actually, we have a comment. This paper is published in Nature. It gives the first information of ventriculation. Yes, there is another equation that explains the Dunn equation, but I don't have access to that. And I'm hoping to learn more of it. We, as folks who work in industry, we don't always have access to academic papers. This is just what we were able to find. But that's it. That's kind of the short of it. And there is just kind of this sliding scale bar between 0.5 and 1 when it's like capacitive and diffusive for Faradaic reactions. So hopefully that helps answer your question, because I think last time I was just showing you what is the case when you have a purely diffusion controlled or a purely capacitive controlled thing. But the pseudo capacitance thing is new and something at least that I'm learning about. And hopefully I'll be able to find the paper that explains the Dunn equation in more detail, sort of say.
So Sharif says this paper published in Nature in 2013. Is that the year of this
Yeah.
Augustine paper? Yeah. So
Yes.
it gives the first information about the intercalation pseudocapacitance of niobium oxide.
Yeah.
There was another paper explained the
And-
Dunn method. Okay, so maybe there's an earlier one. I'm sure somewhere earlier.
Yeah. This was
Presumably Dr. Dunn. So
yeah. Bruce. Yeah. I think it's Bruce.
Unless
Dunn.
it's an incredibly wonderful coincidence that
someone
named Dunn published a paper about the Dunn method, but it's a different Dunn,
which
it's possible.
Could happen, and it's also spelled the same.
Yeah, unlikely, but
yeah. Possible, and there's a lot of things about pseudocapacitance. It's like he's actually talking about the intercalation pseudocapacitance, but there's also like electron transfer pseudocapacitance, Faradaic pseudocapacitance. So there's like multiple different forms of pseudocapacitance, and this specifically applies to very special systems and supercapacitors, and batteries. This is not like your traditional electrochemical, like the stuff that you would find. The stuff that you would find in this book. It's not that kind of stuff.
Yeah, it's a little beyond that.
It's a little beyond
that. Okay, so the last thing that I want to talk about, at least as far as we've got sort of prepared here, and please, if there are questions and folks are showing up, type your questions in to the chat in LinkedIn and Twitter, YouTube, wherever you are watching us. Type your questions if you have any. We'll get to them as soon as we can, of course. There was a YouTube short that you made recently. I want to show it first to provide context. I'm just pulling it up here. Let me just, can you I know it's like a short, you can't always rewind it, but I'm going to see if I can show.
Yeah, you can rewind a little bit of this.
I don't know if it's possible. Anyway, so there's a YouTube short. So if you're not familiar with these, of course, they're, well, as they sound, short videos on YouTube, and it's like less than a minute long. And so
I've been experimenting with them, seeing if they're useful or not. So
it seemed to reach a lot of people, and there was a little bit of backlash is the wrong word, that's too strong, but there was some comments on it. I think folks were not quite understanding, and I want to kind of clarify this. Both of us want to clarify this, but I'll take the lead here and show you this short first of all. So it's titled "Concentration Gradients Don't Cause Diffusion." So we'll just watch this real quick.
Conception in electrochemistry is that the concentration gradient that forms at the electrode surface when a redox reaction occurs causes diffusion of new molecules towards the electrode surface. The concentration gradient doesn't cause diffusion to occur. This is a misconception. Diffusion is just the random motion of molecules. These molecules would move around randomly whether a redox reaction was occurring or not. The concentration gradient forms because a redox reaction is occurring at the electrode surface, but it doesn't cause diffusion. Diffusion is always happening.
Okay, so this caused some people to point out Fick's laws, right? Fairly enough, or right, accurately enough. And so I will show you Fick's laws, right? Let's talk about these for just a moment. So these are Fick's laws of diffusion, Fick's first law and Fick's second law. And so in short, Fick's first law describes how the mass flux or molar flux, however you want to put it. I put moles here. It's typically looked at in mass. I probably should put grams. It's the same thing, obviously.
Yeah, mass and moles.
It's material flux, right? It describes how the flux of materials is impacted by the concentration gradient. So dc dx. The concentration changes with space, with distance. So it's concentration gradients, right? And so basically the mass flux of Fick's first law is equal to minus the diffusion coefficient, which is like a fundamental property of the electrolyte, let's just say, or the material, right? The solution, whatever you're looking at, times the concentration gradient. And then Fick's second law, we're not quite as interested in. It's sort of more focused on the first law, but the second law describes how the time-based change in concentration is related to the spatial change in concentration. So this is the dc dt. How concentration changes with time is also proportionate to the diffusion coefficient times the second derivative of the concentration gradient. Okay. But focusing more on Fick's first law, this is where people, I think, were tripped up. And it's a common misconception, I believe, which is why you're short. You decided to make it. Right. And that is to say, we look at this and it's easy to come to the conclusion, for instance, when I say J is equal to minus D times dc dx, to say dc dx, which is the concentration gradient, well, that causes J because it's on the right side of the equation and J is on the left side of the equation. So they're directly related. And so when the concentration gradient changes, the flux changes. That is, of course, true. That is mathematically true. And Fick's first law describes how they are related mathematically. The key here is a language thing. This is an English language. So apologies if English isn't your primary language. And I mean that seriously. Fick's first law describes mathematically how the flux and concentration gradient are related. It does not describe that one happens because of the other fundamentally or physically. That is not what it says. Okay. So allow me to elaborate a little bit here. You talked about the concentration gradient because of an electrode surface reaction, but I'm going to make it even more simple, right? Let's just say, and this is diffusion, the concept of diffusion in the absence of anything else, no convection, no pressure gradient, no migration, right? So we're just talking about diffusion, which is definitionally the random motion of molecules, which is always happening when you have molecules in the liquid or gas phase primarily, right? Solids, they're sort of vibrating, but let's just say liquid phase, right? To be simple. They're always moving randomly, okay? And we talk about this, we use the term random walk for a reason, because well, we can think about this. Before I get into my diffusion thing, let's write it this way. If I have a molecule, and I'll make this two-dimensional just to make it easy, right? Along a two-dimensional axis, and it's at this position 0. And then there's 1, 2, there's these, there's left and right, like in some unit time, some unit of distance. But we can just draw a simple like number line here, right? So after one time, what the random walk, the way we conceptualize it, is that after one unit of time or whatever, there's a 50-50 shot that this molecule will move this way or this way. That's it. That's what it means. And then if it moved over here, there's a 50-50 shot that it will move back or this direction. And then again, if it moved this way, there's a 50-50 shot. And so it's literally just like this constant probability machine where every like unit time, whatever that means, there's a 50% chance it moves one direction or the other direction. Now extrapolate that to 3 dimensions and it's complicated, but effectively what it means is that there's always a like equal chance that a molecule will move randomly in one direction or the other. That's what it fundamentally, how we conceptualize it, diffusion, which is why it's called random walk. So then consider this simple kind of thing where we have like a vessel separated by a perfectly permeable membrane. Okay. And we have on this side, let's just say we have 4 molecules. Okay. And on the other side, we have 0. Okay. Now, what you would say here is we have absolutely a concentration gradient because there's more red molecules on the left here than on the right. So there's like a concentration gradient that's moving from left to right, like great to small. If you were to track this, there's a concentration. There's a high concentration over here, and there's a low concentration over here. And I'm making it very simple because it's like 4 and 0. Okay. Now consider the random walk. If all 4 of these molecules are right at the barrier between the 2 compartments, then there's a 50-50 shot for every single one of these that they will move in this direction or they will stay in their own compartment, let's just say, right? There's a 50-50 shot for each of these. And so statistically, what does that really mean? Well, after some amount of time, statistically, it means that 2 of these are going to make their way over and 2 will stay or move in the other direction or something, right? Like this is just statistics, like flipping a coin. You could get tails 50 times in a row, but there's statistically a 50-50 shot that it hits heads or tails. And so what is the result of this statistically is that over time, some amount of time, the diffusion gradient goes to zero because now there's an equal amount of red in both compartments and there's no gradient. There's no difference in concentration between compartment 1 and compartment 2. It's the same. But the key here is that this did not happen because two of these red molecules looked at each other and said, hey, look, there's no red molecules over there. Let's go over there and like make it nice and even. No, that's not what happened. The molecules did not move to the other side because there was a concentration gradient. The concentration gradient changed simply because of random motion, because there was nothing on this side. There were no molecules on the right side to randomly move to the other. There's nothing, right? I mean, this is a perfectly ideal situation. There's zero molecules, but like, well, they wouldn't go back because there was nothing there to start with. So by random statistics, they will equilibrate eventually, and then the concentration gradient will go to zero. But then the other part to consider with this, and the last thing I'll say about this, is that again, looking at Fick's law, in that situation where eventually by random statistical motion, the molecules even out and the concentration gradient goes to zero, if dc dx goes to zero, J goes to zero. There's no flux, but the diffusion coefficient is not zero. D is still there. There's still a diffusion coefficient because there's still random motion, even when there's no concentration gradient and no net flux. In other words, the movement, let's just say in all directions, is roughly the same. And so there's no movement like flux of molecules in one direction or another. They're still moving. And the diffusion coefficient captures that. It's the fundamental property that describes like how much molecules are moving per area per time, basically, something like that. Mm-hmm. So when dc/dx is zero, J is zero, but D is not zero. There's still random motion. And so again, just to clarify, the random motion of materials, of molecules, is what defines diffusion. Mathematically, Fick's law shows you how the concentration gradient is related to the mass flux. Mathematically, they are related. One will change. When you have a large concentration gradient, you will end up with a large mass flux, but it is not because physically you have a large concentration gradient. It is because the random motion of molecules will result in a large mass flux. It just will, because statistically that's how it works. It's not because the concentration gradient physically. Mathematically, they just relate that way. So I hope that kind of clears it up. I don't know. Some people may still be sort of,
I think people will still
on edge about this. I know that it's one of these things that feels like, oh my gosh, they're saying Fick's law isn't real or something. That's not what we're saying.
Yeah. And that's I think a good description of it, as well as in electrochemistry, there's also one important thing, which is the fact that the electrode area, like the electrode itself, and the molecules immediately adjacent to the electrode, like they have a different boundary condition because they can only go one direction at one particular point in time, because they can't go, in the case that they're not intercalating into the material, into the electrode, they can only go one direction. But I think almost to go back to, if you want to go back to that picture that you had of the three molecules, if you didn't delete it. Another kind of thing to note is that so the molecules that are on the right hand side will also go back to the left hand side, and the molecules on the left hand side will go back to the right hand side, and they will keep going back and forth on average between these two. And if we added other things, so the point is that I think Neil just kind of described it perfectly accurately. And if we want to make this a little bit more, in a strange way, complex, so actually let me share my screen for a second. So I talked a little bit about, because we do this in simulation as well. So this is so can people see this screen? Yeah. So it says method of finite differences. This is the, like, how did we simulate diffusion? This is like extrapolating Fick's law into reality. And so what we do is to understand what is so to understand this, we're looking at these blocks just represent different slices, if you will, of area next to the electrode. That's what this is. Like your electrode area is here. You have the solution all the way out into over there. We only want to look at the concentration of these species, and then mathematically, we want to know, okay, what is the concentration of this specific sphere at one particular time or at the next time? Well, the concentration of this is going to be equal to what it currently is, so what its current concentration is, plus the diffusion coefficient, effectively the diffusion coefficient or a diffusion coefficient factor, multiplied by the decrease in the concentration of it from kind of giving two pieces, if you will, to adjacent molecules, plus what's coming from this side over, and then what's coming from the other side over. So it looks like this. So when you put that together, this represents the diffusion of molecules from here to here. Again, just a random walk. And this represents the diffusion of molecules moving from here to here. And so that process is just happening over and over again. And so even if we had a super high concentration of species at like Ca J minus 1, and there was less here and there was less here, well, in the net, some of the molecules from here move here and then here, and it kind of trails off as we observe in diffusion. But some of the molecules from here are going this direction, and some of the molecules from here are going this direction, and some of the molecules here are going about, like, they're still doing that, even though we think that it's kind of directional. But diffusion is the thing that's driving this whole process. Like, those molecules are moving back and forth. But when you work the math out entirely, it just looks like it's just going in one direction. Like it's traveling from high to low concentration. But the net is that it's moving in high to low concentration. On the individual time scale level, some of it's moving this way, some of it's moving that way, back and forth. So that's just another thing, all of which is moved in by diffusion. So I'm still on the fence about whether or not, like, is that video too confusing? Am I making too bold of a statement? But
it feels to me like it's a catch-22 in the sense that it is something that is true, what we just described, but it takes time to kind of explain why.
yeah,
When you say something like when you say something like concentration gradients don't cause diffusion,
yeah,
hopefully over the last 10 minutes, we've
Yeah.
just explained why that's the case.
yeah,
It's a YouTube short. It is
yeah,
definitionally limited to 1 minute.
yeah.
So it's not controversial. It's a true statement, but it feels false when you look at it through, like, oh, Fick's law, blah, blah, blah. It looks like it's violating, blah, blah,
yeah,
it's not. But the problem is the ability to explain it in detail is not conducive to a short,
yeah,
which is why
Yeah.
we've done it here. And hopefully what we'll do is, I'm guessing what I'm going to do is make the title of this video explaining why the short is correct.
Oh yeah,
like
yeah,
this live stream is primarily about why concentration gradients don't cause diffusion, for instance. But again, it's to a certain extent, some people took a cynical approach, I suppose, to using a short for that topic. To me, I look at it and it's like it's starting a conversation.
yeah.
Which is always a good thing. More conversation, more discussion, and scientifically is useful. And it gets people thinking about this kind of thing. And even just the fact that some people looked at it and thought that feels wrong to me is helpful, that we're talking about something that's pretty ubiquitous, and it makes us all think about it in a different way.
Yeah.
Or at least in a more in-depth way.
Yeah.
than we might otherwise. I think that's a useful kind of a like impetus, I suppose.
Yeah.
So I would defend
absolutely.
using this short,
The
in that
short
way.
will stay.
It will stand. It remains.
It remains.
They can take our videos, but they'll never take our shorts. It sounds like clothing.
Yeah, that's
They
right.
can take our pants, but they'll never take our shorts.
Yeah.
That's a bad dad. I'm sorry. I regret everything. That was funny.
No.
Yeah. Actually, Sadeep has asked a question we basically just spent the last 15 minutes answering. Can you please explain how the diffusion takes place? Well,
the diffusion and migration.
So I just went on a crusade to talk about that. And describing how diffusion takes place, which again, diffusion in short is random walk. It's random movement of molecules or, item piece things.
Whatever
you want to say. And maybe you can describe migration, I guess. So we just talked about diffusion, just to be clear. So we'll back up the video if you're on YouTube by 20 minutes or something. And I just explained, for instance, diffusion, and I talked about Fick's laws and concentration gradients. And Alex just shortly ago, 5-10 minutes ago, showed simulation and computationally how you handle diffusion. And so hopefully we've kind of already talked through how diffusion takes place, but you can.
And I can like elaborate a little bit, because you might want to know, like, in the context of cyclic voltammetry, how does this work? So
with coefficient values and its mechanisms.
So let me go to this, and we may need to hide the question because of all the stuff. But so this is kind of the method that we use, like, mathematically, of how we approach it. And all these slides here, this is like, there's kind of two factors. There's mass transport, and then there's diffusion. So one way to think about this, and this is kind of how we think about it, is if we have a redox reaction, we have our oxidized species plus an electron gives us our reduced species. The concentration initially is all, and let's just say I have all of the oxidized species in solution. So it's no different than, say, I'm doing a ruthenium hexamine or a ferricyanide reaction, and I just have ferricyanide or ruhex in solution. So all of the cells in my solution look like this, right? And there's none of my redox species, right? And this is at time equals 0, which is indexed. And then Butler-Volmer describes kinetics. So in this case, kinetics is it changes, but like maybe we're doing a chronoamperometry experiment. So I can kind of relate, again, going back to Fick's law. We're just looking at flux at the electrode. So at the cell or at the electrode surface, like 10 to 20 angstroms from the electrode surface, that's when an electron transfer occurs. So we define that cell as having the condition that will always evaluate the concentration of our oxidized and reduced species by the difference of these, the flux, based on the rate constants of the oxidized and reduced species, which is ultimately related to your potential and your E naught and your heterogeneous rate constant. Okay. So this comes from Butler-Volmer. So as we do an experiment, initially what happens is all of the oxidized species at the electrode surface, like, instantly becomes reduced. That's just kinetically, electron transfer is super, super fast, especially on the time scale of diffusion and these experiments, right? Electron transfer is like 1 × 10 to the minus, like 15 seconds, right? And diffusion is like hundreds of milliseconds or something like that, right? So orders of magnitude faster. So initially, at my first time instance, I'm going to have like some stuff going, half are going to go this way, half are going to go that way. And then what ends up happening is like, oh, well, half of this, of my oxidized species, is now going to go in here. So now this is going to start to deplete. And some of this is going to go here, some of this is going to go here. Additionally, some of this is going to go here, and some of this, like, this is the diffusion's always happening. These cells, even the ... cells, they're still going through the same process. And that's the same thing here. like 50-50 this way, 50-50 this way, or 25% and 25%. And then you just keep going. You would keep iterating this, and this is how we create the concentration. This is how the concentration gradients start to form. Is we keep iterating on this process, assuming that at the potential we're running, this thing is completely gone. There's no oxidized species here, and we just have the reduced species. And so flux and the concentration that always gets added gives you the current. So that's how we simulate it, and that's how we think about it, because our simulations are super good, and you should definitely try them out because it's Aftermath Live. So, so that's diffusion. That's how we can think about diffusion. And if you want to relate it even further to cyclic voltammetry, we can start to think about at different times, processes are starting to happen. The potential is becoming more dominant by one side of the equation. As we continue to move on, still the potential says this part of the equation dominates the reduction of our oxidized species. But we're running out of material because this is much lower, and hence the current starts to become more positive. We lose it. But then eventually we start to move back to this region where this side of the equation for the Butler-Volmer starts to take place. And this has been developing as this has been, going down. So now this side from the potential starts to dominate. And as you continue, as you continue, you'll start to deplete this again. And when you put all this together, I'll just share some of our simulation stuff, because why not? Always want to promote that. If I do a simulation of a cyclic voltammogram using Aftermath Live, and we're doing just very simple electron transfer kinetics for a good redox species, and I simulate it, and I'm looking at the concentration profile, and if I run it, you have your species here. That's what we have in concentration. And then as we start to approach the E naught, it starts to go down, concentration decreases. This is the length, the distance from the electrode surface. So the simulation is just running through this entire process of like, there's a little bit of this constantly moving this way, but it's lower and lower. And then eventually we reach a point where kinetically it inverts, and then they start to go back to normal but kind of deplete. There's like different concentrations away from the electrode surface. So that's diffusion. That is describing this whole process via a diffusion controlled process. The only thing I'm going to describe about migration is that migration is, let me bring up this is the Nernst-Planck relationship, which describes the flux, the movement of molecules. It just describes only mass transport of molecules in solution to an electrode surface, in our case. Green is the diffusion, red is migration, and then the purple one is convection. So I actually don't know enough about migration to provide a detailed analysis of it. But in general, one thing that's very important to note is that migration has always been limited because we add a sufficient amount of supporting electrolyte to our electrochemical system. It decreases the field effect, and I think, I don't know, Neil, if you want to talk. There's an equation, or there's a graph in Bard and Faulkner that I can look up that
for
basically
migration?
It describes it describes how the it's not the concept. It describes how the field. Actually, maybe I have it as a PowerPoint as well. But
I don't know if I have anything for that.
Let me go to, because I think this will still be useful if I just show. Let me run. Give us a second. Give me a second. Because when I originally saw this, it blew my mind. So let me share this this slide. Okay. So this slide, this is looking at the potential versus distance from the electrode surface. So this is kind of you can think of it as like the solution potential, and this is the potential that you apply of your metal
Mm.
electrode. When a molecule so the main takeaway from this kind of image um, is that the potential drops very very quickly as you move away from the electrode surface, very very quickly. So this is like the inner Helmholtz plane. So that's like the locus, like the locus of the plane that's centered to adsorbed ions or anions in this case, next to immediately adjacent to the electrode surface. So we're talking about like angstroms here in terms of
Mm.
distance. And then the outer Helmholtz plane is similarly like the next kind of level of next approach, sort of say, of the next layer of ions here. Um, Again, I'm talking about the electrical double layer. If it wasn't clear, um, and and so a molecule's got to get super close, within like 120 angstroms of the surface, to gain an electron through a homogeneous electron transfer. So that's really close, right? That's in this region. When you have low supporting electrolyte, this tends to go something like this. The field effect that you're applying is kind of spread out,
Mm.
and migration becomes a bigger factor if you have a charged molecule that you're doing redox chemistry on. It'll start to feel the field effects. Um, exactly how, and also it changes the double layer structure. This is no longer the same double layer structure when you don't have enough supporting electrolyte. So, um, the truth is, I don't know enough about how migration like mathematically is like changes the how it changes the system, or like the electron transfer, but generally speaking that's what we think about. Like migration will happen in this region if the supporting electrolyte is too low, because the field strength uh is it's the same field strength, but it's dispersed over a wider or a bigger area. So you end up getting interesting effects. I'll just leave it at that. So Sudeep, I hope that that was helpful. Please let us know if it was, and and if you have more questions, we can try to address them.
So Harini has a question. What is the R squared regression coefficient? So generally
Mhm,
speaking, if you're just asking what R squared is, I guess, I don't know if you're
mhm.
asking with respect to, like, for example, impedance, goodness of fit has a error statistic associated with it. Very generally, R squared is a statistical phenomenon. It's not specific to electrochemistry. But in all cases, when you have an error statistic, it tends to be something like this, which is if I have just X, Y, so just regular Cartesian
Mhm.
coordinates. Um, for instance, I have Y is the dependent variable and X is the independent variable. So it doesn't matter what these units are. Independent. So one variable is independent and one's independent. All right. So we have data points like this, and we do a regression to get a fit. It doesn't matter whether it's linear or non-linear. We'll just do linear for simplicity here. And we do a linear regression and we do a fit and we get this line that goes through it. What the R squared is it's a measure of effectively how far the red is from the blue, how far my actual points are from the line. In essence, it's a bit of a somewhat complex mathematical assessment, but you can imagine at every point where I have a red dot, if I draw a straight line to the blue line, Okay, right? These are distances. Like this green, this is like distance 1, this is distance 2, distance 3, etc. So what I'm doing is I'm taking the sum of all of these distances, d equals 1 to however many there are, and it's basically d squared. So that's the first part of it, is I'm basically squaring the distance. And then I don't want to get too mathematically complex here. It gets a little bit hard to conceptualize. Basically, the r squared is 1 minus the residuals squared. So that squared divided by a different sum, which is related to the mean. It's the average. But basically, effectively, you can see if, for example, all of these red dots were on the line, all of these D's would be 0, right? There would be no green lines. They'd all be 0, right? If all these points were right on the line, it was a perfect thing. So that would go to 0. And so r squared would be equal to 1. So r squared of 1, or 100%, if you will, basically means that my fit is perfectly through my points. The interpretation of when r squared is not 0, so this might be like, for example, with the first example I drew, let's just say r squared ends up being like 0.95. What that means in some way of speaking is that the deviation of my points of my dependent variable y are the variation in them is 95% accounted for by the independent variable. And there's 5% deviation, essentially. That's just accounted for that's error, if you will, something like that. So the r squared, the way that it's understood, is that it's like you want it to be as close to 1 as possible to indicate close fit. And this would mean that there's 5% deviation, if you will, between the correlation of the independent and dependent variables. But again, it's largely, without getting too much into the math of this bottom sum, it gets a little kind of complicated. It's hard. I find it hard to conceptualize. Like it's the difference between each of these points and the average of each of these points. And it's like, well, the average is what, like over here, it's in the middle somewhere. And then why are you doing that? It's a bit hard to conceptualize, I think, like that part of it. What I do find easy to conceptualize are just, you can think of it as just some physical measurement, numerical measurement of the distance of each of these red dots to the line. That's essentially what it's measuring. Like visually, you can kind of see that. It makes sense to me. And so the error statistic, for example, in impedance measurements is related to these distances. So when it gets higher, it's bad. The r squared is more like 1 minus that. So when it's high, it's good. It's just whether it's between 0 and 1, or if 0 is good or 1 is good. It just, sometimes you look at it as like 100% means really good, or 100% is like 100% error. So it's just like the order is backwards. So r squared is where 1 is a good thing. 100%, it means the error is low. And then like a lot of times the chi-squared works the opposite way, where the large number is bad because it's like adding up all of these green lines. And if they're too big, it's high, something like that. So hopefully I kind of, a little bit of an explanation of how that works or what it is, I guess. It's a bit of a complicated, somewhat like mathematical concept, but hopefully that kind of clarifies it a little for you.
Yeah.
So
we just got a question from Amna, who's saying, kindly tell me about the range of values of ECSA, electrochemical, ECSA, electrochemical active surface area, for effective catalyst working. I'm not so sure. I think
boy, it really varies.
Yeah.
First of all, if you're asking about the active surface area, Well, it depends how big your electrode is. I think
Yeah.
in a lot of cases, for instance, if you have like a small film or something like that of your catalyst, and you have a geometric surface area, the ECSA is often and hopefully larger than the geometric surface area. Maybe it's 1.5 times. So if you have like 0.2 square centimeters, maybe you'll have like geometric area. Maybe your ECSA will be 0.4, and that's twice as big. And so that's good. It means that your catalyst is quite active. There's a lot of more active sites than geometrically would suggest. But it's like you can't really give an answer to this like 1 square centimeter, because it depends how big your electrode is. You know what I mean?
Mm-hmm.
It's not a universal value. It depends how big it is. It just depends on how big your electrode is, and then the microstructure essentially, and in some cases it's like the facet plane of platinum. Like, is it platinum 110 or platinum 111? Some of these are more active than others, and some will have a higher ECSA than others. And it's really more about the ratio, for example, right? It's like if your ECSA is identical to your geometric surface area, like that's one thing, right? That's good or bad depending on what you're looking for. But in a lot of cases, it's like the ECSA is some multiples bigger than the geometric area, and that is maybe good or bad. Often good is what you're looking for to improve the quality, the activity of your catalyst, to see how well it performs whatever reaction.
Yeah. I mean, like effective catalyst working, like how efficient is your catalyst, is like the ECSA is part of the calculation of determining if your catalyst is effective or working. Um, so you put, maybe a weight percentage of your catalyst on a substrate, and then you try to do catalysis. You use the ECSA to just figure out like, okay, well, what's the current density that you're getting? Like, what's the current divided by the area, and the ECSA is that area. And if you are getting more current per unit area for one catalyst versus another catalyst, then you have a more effective catalyst. So, I I guess in a certain way, you want to have low ECSA values if your catalyst is really good, because that means your current density is high. Um, but I'm not so sure if that's exactly I don't know if that's exactly what you're asking for, but that's kind of our quick answer for you. Um, we have a couple other questions.
Yes, Sneha has asked, please suggest some interesting area to do research using hydrogen evolution or oxygen evolution. And they said that they're currently working with polyoxovanidate chemistry. I mean, I don't know what you area to research. HER and OER are areas of research. I don't know if you're asking about a specific subset of OER, HER or something. I guess I don't totally know what you're
Yeah,
asking about. I mean, are you trying to do OER with these polyoxovanidates? I mean, I assume you're
yeah.
working with like maybe vanadium flow batteries or something. I mean, I don't know any other real application of vanadium type catalysts, although I'm sure there are some. I don't. Yeah, this is. I mean, this is a hard question to answer. I mean, there's a lot of OER, HER research out there. People are trying to maximize catalyst activity or reduce overpotential. Study the amount of current or material product you can drive, like how much hydrogen or oxygen can you generate per time or at whatever potential. How effective is your catalyst at performing OER, HER? I don't know if that's exactly what you're trying to do. I mean, you could start there, take your catalyst, devise a cell where you can perform electrochemistry there using cyclic voltammetry or linear sweep or EIS or all of the above, and see how much current you can get, see what the overpotential is, see what the onset potential is, see how effective it is, connect to a gas chromatograph maybe or a mass spec and see how much product you're getting, see
Looks like they're saying I'm asking more specific area of research using HER, OER. More specific area of research using HER, OER. One guy was literally just asking about like a nickel catalyst. You could start studying nickel catalysts in alkaline solutions or something like that. Um, so yeah, I mean, you could just like, do you just want to pick like a different kind of metal and then do those kinds of things? I I don't think Neil and I have either done a lot of research. Like we know about HER and we know about OER in a general sense, but we haven't dived deep into like a specific subsection of HER or OER. I
Yeah,
think it may also depend if you're like into the engineering, right? You could look at it from like the
yeah.
fuel cell perspective, um, or
I mean,
or
I
something
guess
like that.
I don't even really understand what is more specific. What is a specific area of research using like OER and HER are research topics. They are the specific areas of research through which like many people base their entire PhD, for instance. Like it, you know,
Like
the,
maybe do you want like a
I
material?
don't.
Like, do you want us to tell you like look up some iridium complex or something for HER applications?
Yeah, I don't know.
You
Yeah,
know,
if you're asked, yeah, maybe if that's the point, if you're asking
yeah.
like what is the
What's the
most promising material to be used, or what's the state of the art, or what should you use to study it, it's like I don't know that we know the answer to that question,
Yeah, a
right?
little bit too specific.
Yeah, and the research is changing all the time, and there's lots of
Yeah.
publications constantly, and obviously we don't have like intimate perfect knowledge of what everybody in the most up to date research is
Mhm.
using for a catalyst for this or catalyst for that, or precisely what is being used. That would be something, and to be honest, a lot of the time, like what you are sort of looking at studying when you're in graduate school, for instance, or even as a postdoc, is predicated on like what your advisor or your group or your PI is tasked with, or what they're
Yeah.
like just as an example, I studied lithium ion batteries when I was in graduate school, um, and I was interested in batteries, and I did it to a large degree because I like batteries. They fascinate me, but mainly what I studied was nickel and nickel oxide as alternative anode materials for lithium ion batteries. And do you know why I picked nickel? Because nickel was part of a project that my advisor was doing on a different thing. And then it became evident that, hey, nickel works on batteries. Let's study that. I didn't necessarily pick nickel because, it's like, despite the introduction that you write in like every publication where you say something like nickel is a promising catalyst that's receiving lots of attention in recent years because of XYZ, and then you cite 20 different papers of people that have done it or whatever. It's like most of the reason why those people are studying nickel is for other reasons, not necessarily just because it's an attractive material. It's because you just had
They
some
had
you had
some.
some
Yeah.
nickel oxide in a container in your salt shelf, and it was like, hey, let's just try this. It's like, right, I mean, no, I'm being a little cynical here, and perhaps there are other reasons why people do really scour through the periodic table and figure
Mhm.
out this or that, or okay, fine. But like sometimes that's just what happens, is you just look through the literature and find people are studying iridium oxide or palladium, platinum, whatever, and it's like, well, I just want to study that too. Or, well, what if I made an alloy of these two and see what happens? Like
Yeah.
sometimes that's the answer of like what specific material you should study, but that
Mhm.
isn't something that we can really answer easily, just because we're part of the problem again is we're not in academia, and we don't have a perfect beat, for example, on like, let's say, the last 3 years of HER research. Like, what exactly are people finding?
Yeah.
Where's the state of the art now? That's hard to keep up with.
Mhm.
Heck, it's hard to keep up with in some sense, even when you're in academia, let alone when you're in industry like we are, and we don't have as much of a um, tie to the academic literature and how it evolves over time. So,
Mhm.
I would encourage you to just, find a literature survey of like 100 or so papers over the last 4 to 5 years and see what people are using. See if you find any trends. See if you find any materials that seem to be pretty ubiquitous, and try to make some yourself. I mean, start with what others have done. Start with some material that you can compare to a literature, and then branch out on your own. Well, what if I add, 10% platinum into this, or palladium, or ruthenium, and see what happens? See if that improves. What if I have a morphology that's a little bit different? What if I engineer the catalyst and the cell in a different way? What if I don't know, think about some of the places where people in the literature have not tried yet, or and that's kind of where you might consider going after, because that allows you, for instance, if you're trying to get a PhD or even a postdoc, to publish papers that say things like, lots of researchers have tried X, Y, and Z, but they haven't considered this particular variable, and so we did, and here's our results. Something like that. So yeah, it's
I think so. Yeah, I think it's a good thing. So just going in order, there's a question from follow-up question from Harini. He's asking, can you tell me how to find or calculate theoretically? I think it's supposed to be HOMO-LUMO gap. And so HOMO is highest occupied molecular orbital. LUMO is lowest unoccupied. Highest occupied, lowest unoccupied molecular orbital. So I don't know enough about the theoretical calculations. I think there's a lot of computing software that can be used to try to figure out what that gap is. But generally speaking, in a very general sense, most people use UV-Vis spectroscopy. We're usually looking at HOMO-LUMO gaps for inorganic complexes, things like that. And so doing UV-Vis, and I'll just draw this very quickly. It's not so much electrochemistry, but slide. So it's not really electrochemistry. It's actually more on the lines of spectroscopy. But if you have your so if you have your highest occupied, just do this HOMO, and then you have your LUMO, which is here. Generally speaking, you're trying to figure out what the energy difference is from here to here. Well, most of the time, people will actually just shine light. That's supposed to be a photon of light to excite an electron to the excited state, and then upon relaxation, it'll come back down, and then it'll emit that photon of light to a detector, and then we can see in the detector and a spectrograph and all those types of things, and generally you get some kind of spectrum where you have like wavelength. Length.
Writing is so much harder than you think it should be.
Oh, it is.
With a mouse.
Yeah.
The letters don't always look good.
Yeah. Wavelength in something like nanometers. And then, God, okay. And then this is like absorbance. Abs. And, you get something that looks like this. And it'll look a little bit funny, there'll be some noise in certain areas. But like, this is this peak here corresponds to this transition, ideally. And then once you know the wavelength, you can use the Planck's relationship. I forgot the equation, but it has like the speed of light, the wavelength, and Planck's constant, and you can convert that into energy. And that is a way to get the energy of your HOMO-LUMO gap. That's mostly all I really know. I don't think electrochemically, to my knowledge, you can measure the HOMO-LUMO gap. You mess around with the HOMO and the LUMO, but you can't isolate their kind of either individual energies or their energy difference electrochemically, at least easily.
Maztastic
Fantastic.
has asked a question that I don't know that I'm very adept at answering. And please
Yeah.
enlighten about upcoming biosensor research field, future job market for biosensor graduates for PhD. I don't know, to be honest. I know biosensors very broadly are used or studied for like drug detection, um, uh, uh, things like checking for various antigens or pathogens. I don't know, maybe checking like blood glucose levels for diabetes, folks with diabetes, or other you know illnesses or sicknesses, I guess that have markers in like the bloodstream, for instance. I think that you can do stuff like that. I think there's other sorts of people that are doing some cool research I've seen here and there, I suppose I'd say, about biosensors. Like, let's say you want to check for something on your skin. You can put like a biosensor on your skin. It will measure like the salt content or the sweat. So there's things like that. A lot of other sorts of research that's going on, I think, in that regard. But as far as exactly the like level of research, I don't have any personal experience with biosensors, so I don't know that I can answer that with much authority. And then as far as the job market, I also don't know if I can answer that with much authority, because I don't know a lot of the I know there are biosensor companies. There are like, certainly companies making or doing, and again, it sort of depends. It's like, there's probably a good amount of startup companies, for instance, that are trying to commercialize certain technology, I suppose. This happens, right? It's like a professor or someone in university or an academic field might have a good idea, and proof of concept research shows that it would work, and then you make a startup company and try to get funding and see if it works. Okay, so there might be job prospects in various startup companies with biosensor technology, so you have to look for those. But startup companies can be tough because a lot of them do fail. To be honest, they don't all make it. It's tough sledding. I'm just being honest about it, right? It can be an exciting opportunity to work on something cutting edge, but commercialization and penetration into the market is difficult, right? You have to be profitable eventually, and so that can be hard. So it's an exciting, fast-paced kind of a thing, but it doesn't always necessarily lead to long-term job security. So it's a trade-off for folks who are looking for that kind of that kind of work environment. And then I guess, very generally speaking, if you're working in biosensors and electrochemistry, there are plenty of jobs, for instance, where you might pivot to a slightly different or related field that uses electrochemistry, but it's not specifically biosensors. I studied mostly batteries, and I don't work for a battery like specifically battery company, but Pine makes electrochemistry equipment, not specifically batteries. So it's like there's a parallel move, right? I could have gone to work for a company that makes batteries or does research on batteries, or I could have joined a lab that's doing battery research, and I joined a company that makes general electrochemistry equipment instead of battery only specific. So, so there's other things like that. You might be doing biosensors, and then you move to look to get a position in a research position or a lab position or something that is studying I don't know, some tangential field. I don't know, right?
I think also biosensors. Well, first off, in general, what you do in your PhD research rarely always translates directly into like a company job, and most companies are usually hiring PhDs because they're like problem solvers and have maybe some tangential experience.
Yeah.
But it's never the case that it's like, oh, this is like a direct, like exact match of like, oh my God, they actually studied this very obscure electrocatalyst thing, and we're going to be using exactly that one. We need them.
That's rare. The only exception is if you become a professor and start your own research project, continuing that exact obscure thing.
Yes.
That's not a job in an industry though, right?
Yeah, that's not a job in an industry. But if you're doing, and so I guess I'm assuming that you're doing electrochemical biosensor type of stuff. but you may find the pharmaceutical industry just needs people, in detection. So you may just find a job at pharma. They may just want to know somebody who has some general biochemistry experience, or has some experience putting, RNA on a chip or something like that. So it might not be exactly what you're doing, but it can be related or tangential. So hopefully that is helpful. And I think to kind of address your other question, what are the most prominent or the most prominent skillet for a biosensor graduate target company job? So the most prominent skillet would be this one. This is
Skill set. Oh, skillet.
so
Prominent
these are
skillet.
the classic cast iron skillets. This is what you need.
I'm like, what are you doing?
That's what you need to do this. I'm just joking. I had to. I was like, skillet. Probably skill set.
That's a dad joke for your Friday. Yeah. So it's the
Yeah.
prominent skill set. So other than making, breakfast in the morning for yourself, I assume you mean skill set. I mean,
Yeah,
honestly,
yeah.
you can take out the idea of biosensor from this because to a very large degree, it's just as you said.
Mhm.
With a PhD, my advisor, for instance, when I was in graduate school, used to say that it's called a doctor of philosophy for a reason.
Mhm.
Even though you're doing research and scientific analysis, you are actually not learning science. You are learning how to think. You're primarily learning how to think, how to solve problems, and how to conceptualize a path to do research. But it's a thinking philosophical degree, even though it's in science, chemistry, chemical engineering, whatever it is. Um, the word philosophy in PhD is intentional and meaningful, in my opinion. So the skill sets that you're developing when you do your PhD are how to think through solving problems, how to think through um, uh, the methods and the mechanisms that you would use. My advisor used to kind of differentiate between a master's and a PhD in this way, where a master's degree is getting very good. You're mastering, just doing something and getting very good at that. And I'm not trying to to throw shade, as the kids say these days, on that. That's a very useful thing to know how to do, is how to do a process, like do this lab research kind of skill very well. Like you master that. But the PhD is a step forward, because you also get mastery, for instance, of research and how to do certain things, but you gain the philosophical ability to think critically about how and why you're doing what you're doing, and why did it respond this way. That's why you publish papers or give presentations and discuss your ideas as to why you saw the results that you did, rather than just doing them. Now, obviously, it's not like no master's student ever thinks about why things happen. I'm not trying to say that. It's a one is all one and all the other.
Mhm.
It's just, this is a thing to think about when it comes to a PhD. So when you're looking for a company, right, and you're interviewing with a company, and you have a PhD, or you're getting a PhD, they're going to want to know that you can think that way, that you can operate that way, that you have that kind of level of inquiry and problem solving that is associated with someone who has a PhD. And then what comes with that, probably because you're spending 4 or more years, is the ability to know how to operate complex research equipment, XRD, XPS, TEM, BET, uh, uh,
A potentiostat.
a potentiostat is electrochemistry. Yeah, that one's kind of a big deal.
Oh yeah.
But all these kinds of analytical techniques, whether it's physical characterization, right, crystallography, spectroscopy, electrochemistry,
Mhm.
right, operating these equipment involves using a lot of different pieces of equipment, a lot of different pieces of software. Um, and those are things that a company will be happy to see that you know how to do, that you know how to use characterization equipment, and you know how to operate, and the fundamental concepts of how they work and why they work and things like that, and what they're telling you when you get those data. So all of those things are things you're going to put on your resume. Like, I know how to do these techniques. I know, I've done these types of topics. I studied this particular system, but I know how to do these um, analytical techniques. I did that on my resume, for instance. I used to list like all the techniques that I used in graduate school, and it was a
Mhm.
billion and a half 3-letter acronyms. SEM, XPS,
Mhm.
TEM, XRD, all these things. So, so those are the skills you're going to do. And then, the last thing I'll say, for instance, is that whether it's a biosensor specific thing or it's just a job in general kind of a thing you're looking at for yourself, don't discount anything that you do. Like, I mean, anything. If you spent like one day in like 35 minutes doing NMR, and that's all you ever did for NMR on your entire PhD, but you did it, and so you have some knowledge of NMR, then you write that in your resume or you mention it. You don't know what thing or skill or experience or collaboration that you have throughout your PhD that will lead to an opportunity. Don't discount anything. Write down as you go all of the different things that you do. Don't wait until you're graduating and then you're like reminding yourself, like, what did I do like 3 years ago? Did I do that technique? Did I do this? Write it down as you go.
Mhm.
And keep a Word document or keep it on your phone in a sticky note or something. Like, here's the things I know how to do. Here's the techniques that I got. And maybe it's easy for you. You remember, you have research, you have presentations, you can pull it up what you have done, but keep a sort of a mental or even a physical list, like on your phone, of all the stuff that you know how to do, because you never know when you are applying for a company, you're talking to someone, you're at a conference, you're at a networking event, and you sort of say the magic word like, oh, I've done this or that. And then they're like, oh, you know how to do NMR? And you're like, well, I have some experience with it, and you don't have to lie, but you did a little bit, they might be like, well, we're actually looking for someone who has these kinds of skills. And then suddenly you have the skill set that the job is looking for, and you have a leg up amongst all your other competition. Right.
Mhm.
So keep those things in mind. It's my advice.
Yeah. I think the only thing I would add is so those are a lot of like, technical skills, but there's a ton of just like um general office skills, sort of say, writing, as well as literature, or not literature, reading. Well, read, you can't put reading as a skill, sorry, but like writing, public speaking. You will, even if they just shove you in like a closet and give you and feed you samples that you need to analyze, you still have to talk to people.
Mhm.
um, and so that means also working on soft skills, sort of say. And I generally tell people, hard skills are like, the technical stuff, but soft skills is like, how do you interact with people, how do you, appear charismatic or something like that. um, but the soft skills are the skills that are hard to learn.
Yeah.
Hard skills, by comparison, it's like, well, it's much easier to learn how to code than it is to get you to, be nice to people or open doors for people. But you do need to, call upon also working with people in a team. Neil and I both did our PhDs, and we have our own individual thesis, but now in the company, we work together and we work with other people together. So you also need to be able to do that. And
And show examples of how you did
yeah.
that. So yeah, so even to that point, that's a perfect point. And
Mhm.
if you haven't had the opportunity, find an opportunity, for example, in your current lab to just do a little bit of a project with one of your lab mates.
Yeah.
Don't silo yourself, because you will get that question. It's a good point in an
Yeah.
interview. Like, where did you ever have working with a team, and show and describe how
Yeah.
that opportunity went?
How did you resolve a conflict between you and like a team member
I
or
punched him
something?
in the head and I did what I wanted to do. That's not a
Yeah.
good answer,
Yeah.
right?
uh,
Yeah.
yeah. Have these things. Let's see. Oh, Mastastic has a response. It says, recently I'm focusing on detection of colon cancer cell from complex sample matrix blood using electrochemical techniques. It's quite complex, so it's fun to solve. Yeah, no, that's good. And all of your experience with like troubleshooting stuff is going to be very, very helpful, for
Mm.
jobs that you will apply for, and stuff like that.
Yeah.
But but yeah, I'm actually that background. You can you can go into electrochemistry things. I mean, there's a whole bioelectrochemistry thing, not simply biosensors, but just even um,
Yeah.
just bioelectrochemistry. There's also just you could go any route. Like there's a whole like cancer research.
Yeah.
Tons of people just like electrochemistry is the tiny thing off to
Yeah.
the side.
Or here's another example. Like actually, there's a lot of discussion now. I don't know where you are, of course, but
Yeah.
here in the U.S., we have a real problem. For instance, in some of our waterways, environmentally, are polluted. Uh, not polluted like they used to be like 100 years ago, but they're contaminated with what sometimes you call forever chemicals or
Oh yeah.
or
PFAS.
PFAS. Thank you. Yeah,
Yeah.
polyfluoroalkyl something.
Uh,
I should know that more better. I'm a chemist.
yeah. Polyfluoro, maybe aromatic something.
I thought it
I'm
was
not so sure.
alkyl
Maybe
sulfonic something. I don't know. Anyway, what the
It's
point
okay.
is that right? It's like just industrial processes or whatever else have over the years in some places resulted in um, moderate, let's just say, levels of chemicals that we know are probably harmful or we ought to not have, and we want to try to get rid of them. And there are some companies, for instance, there's one somewhere in the northwest of the United States. I think they're in Washington or Oregon, I think, and they developed this um, big reactor that they can take on site to like a river or a stream, basically, and just filter the um, chemicals. Like it works with electrochemistry, for instance, and I think it does anyway. I'm pretty sure. Something about the name of the company inferred that they obviously don't tell you what their technology is because it's proprietary, but it breaks down the bad stuff,
Yeah.
whatever, in some way. So that's another that's just one that came to mind. Like that's, you're in South Korea. So again, perhaps, I don't know if South Korea has the same or different. I'm sure there's, I don't know much about the similar sorts of goings on in South Korea. Of course but there's probably some similar,
As a second-year PhD researcher,
Yeah.
so you've also got a fair bit of time,
to
as
figure
well.
this out. So yeah,
So yeah, but it's not a bad thing to start thinking about jobs. That's actually a very, very good thing. And so yeah, I thought like, oh, you already have like a PhD and you're doing stuff. I would also, if I were you, I would just network as well. Just network as much as you can. Try to go to conferences, talk to people.
Don't discount any skill and don't discount any relationship.
Yeah.
Always, put your best, like, present yourself well in all instances where you're meeting somebody.
Yeah.
You never know who might know somebody who knows somebody who knows somebody who gets you a job.
Yeah.
In the future. And they like met you somewhere and you were very competent and kind and you know how to speak to human beings and those things lead to jobs.
Yeah.
So
Yeah, no, that's true. Yeah, I'd say maybe you could work for our South Korean distributor, maybe in the future. Well, yeah, you have some time before you can do that. But yeah, well, hopefully that was helpful. I think best of luck. You've got a lot of time. Not a lot of time, but you've got some time on your hands.
At least a couple of years, I would guess.
Yeah, a couple of years,
which is more than zero time.
Yeah. So a couple of years is more than zero.
It is. 2 is greater than 0.
2 is greater than 0.
Because you know what? I know how to read and write.
Yeah.
I'm literate. That's how I got my job.
Yeah.
I went to the interview and they were like, "Do you know how to read?"
Yeah.
And write? And I was like, "I think I do."
Yeah.
And they're like, "You're hired."
Yeah.
It's that easy. It's that easy. That's all it takes is literacy. Yes. It's a little known skill.
Yeah.
All right. Well, I think we're going to wrap it up there today. So yeah, this is a different time slot. So for those who are watching this later and you're wondering why you missed it, it's because we changed the time just to mess with everybody. I know the morning slot is perhaps helpful to folks in Asia, because the time difference, of course, is less crazy. But we will probably go back to our normal time slot of 1 p.m. Eastern U.S. time in the future. And anyway, I guess that'll do it for another episode of Ask Us Anything About Electrochemistry.
Yeah. And just for those who watch later, I think the 15th next week will be the regular time. The 22nd, The week after that, the last week of November,
Yeah, we will not be
we
here.
probably will not be here. It'll be Thanksgiving. We'll remind you about that again. And I don't know because the 6th is
I'll
the
probably
MRS
be
meeting.
back.
You'll be back.
MRS is
I should
usually
be back
over.
too. Okay, yeah,
It's usually over over to Wednesday.
yeah, Wednesday or Thursday.
Yeah, there's a conference
Yes,
the
yeah,
first week of December, but it's usually over midweek, so I should be back on Friday.
yeah.
So
Okay.
yeah, we'll probably do this. We'll skip.
Mhm.
We'll be skipping the week during the
Mhm.
U.S. Thanksgiving holiday.
Mhm.
We will probably end up missing 1 or 2 weeks. I would guess around the Christmas and New Year's holidays
Yeah.
at the end of December, as most people are on holiday anyway around the world. So even for that perspective, but
Yeah.
But otherwise, this is our we'll be back next week. We'll try to keep this going. And
Mhm.
anyway,
All right.
thank you everybody, and I
All
hope
right.
everybody has a great rest of your day and weekend.
All right.
Take care.
Bye.